Imagine trying to understand the complexities of a bustling city like New York. Now, imagine trying to do so by scrutinizing the individual apartments and their occupants. That's essentially what understanding electronic configuration is like. It's about deciphering the arrangement of electrons within an atom, providing key insights into its chemical behavior. Just as the arrangement of apartments in a building dictates its functionality, the specific arrangement of electrons within an atom determines its chemical properties, how it interacts with other atoms, and ultimately, the world around us. Electronic configuration provides a systematic representation of this arrangement, allowing us to predict and explain the fascinating world of chemical reactions and the properties of matter. In essence, electronic configuration is the atomic equivalent of a blueprint, revealing the fundamental structure that dictates an element's place in the grand scheme of the periodic table and its role in the universe. The periodic table, that iconic chart gracing the walls of science classrooms worldwide, isn't merely a random arrangement of elements. It's a masterpiece of organization, with each element's position determined by its electronic configuration. The periodic table structure is a testament to the power of understanding electron arrangement. Elements are grouped by similar chemical properties, which stem directly from their shared electronic configurations. For instance, the alkali metals residing in the far left column all possess a single electron in their outermost shell. This shared characteristic explains their similar reactivity and their tendency to form compounds with halogens, which conveniently reside in the column second from the right. The periodic table's organization is a powerful testament to the importance of electronic configuration. It allows us to predict an element's chemical behavior and its potential interactions with other elements, all based on the arrangement of its electrons. Now let's delve into the specifics of electron arrangement. Electrons within an atom are organized into shells and subshells, much like residents occupy different floors and apartments within a building. Shells, denoted by principal quantum numbers, and equal sign 1, 2, 3, represent different energy levels within an atom. Lower numbered shells are closer to the nucleus and have lower energy, while higher numbered shells are farther away and have higher energy. Within each shell, electrons further organize themselves into subshells, designated by letters S, P, D, F. Each subshell has a specific shape and can accommodate a limited number of electrons. The S subshell is spherical, the P subshell is dumbbell-shaped, and the D and F subshells have more complex shapes. Think of shells as floors in a building, and subshells as different types of apartments on each floor. The arrangement of electrons within these shells and subshells determines the atom's stability and reactivity. Section 4. Guiding Principles of Electron Arrangement. The arrangement of electrons within shells and subshells isn't random. These rules, known as the Aufbau principle, the Pauli exclusion principle, and Hund's rule, govern electron arrangement. The Aufbau principle dictates that electrons fill atomic orbitals in order of increasing energy. The Pauli exclusion principle states no two electrons can have the same set of 4 quantum numbers. Hund's rule states electrons fill orbitals singly first, with parallel spins. Section 5. Electronic configuration in action examples. Let's look at some examples of how electronic configuration plays out in real elements. Take carbon, the backbone of life as we know it. Its electronic configuration is 1s2, 2s2, 2p2, meaning it has 2 electrons in the first shell and 4 in the second shell, with 2 in the 2p subshell. This configuration, with 4 electrons in its outermost shell, makes carbon incredibly versatile, able to form a vast array of compounds by sharing electrons with other atoms. This is why carbon is the foundation of organic chemistry and the building block of life itself. Similarly, the electronic configuration of sodium, 1s2, 2s2, 2p6, 3s1, explains its high reactivity. With just 1 electron in its outermost shell, sodium readily loses this electron to achieve a stable configuration, making it highly reactive with elements like chlorine that readily accept electrons. By understanding electronic configurations, we can decipher the chemical language of the elements and comprehend the intricate dance of atoms that shapes our world. Section 6. Electronic configuration, the foundation of chemical interactions. Electronic configuration is more than just an abstract concept confined to textbooks. From simple molecules like water to complex biological reactions, Electronic configuration is pivotal. It underpins advancements in materials science and nanotechnology. In conclusion, electronic configuration unlocks the secrets of the elements.